I want to do a short intro to the idea of velocity, and maybe I'll mention acceleration as well, for a parametrized curve in 3 dimensions. So we want to think of this as the motion of a particle in time. And if we're looking at the motion of a particle, one of the most interesting things obviously is how fast it's going and what direction. And the combination of that, of course, is called velocity. So if we look at our helix example on the default on this MIT applet, then we can, by changing the slider, we're moving the particle that's at the tip of that position vector. And I mentioned that one of the advantages of thinking of that as a moving vector instead of a moving point is that everything in sight is going to be a vector, and we can use the same technology to describe all the things we're talking about. So if we want to get the velocity, what we'll do basically is we'll pick a time, like t equals 1 maybe, and then we'll compare that vector to what happens if I just go up a little bit in t. So we know that subtracting vectors is putting another vector between the tips of these two guys, so it shouldn't be surprising the velocity vector shows up in that direction. Now it shows up rather bigger because I just toggled between 1 and 1 and a quarter in t, and so that's how far and fast it would move in 1/4 of a second. If I extrapolate that, I'm going to get something that's 4 times as long as the velocity vector. Now if I look at the function for this, cosine t sine t t over 4, the great thing about all the stuff in this chapter, as I said a couple days ago, is that the derivatives are really easy. If I want to get the x component of the velocity vector, that should be according to the x direction, how fast is the particle going. Makes sense that that's going to be just dx dt. Take this function cosine t and take the derivative of that. Similarly, dy dt, dz dt, those are the 3 components of the velocity vector. So taking the derivative of a vector valued function is really easy. You just do it component-wise. You just do it in each of the components separately and then put them together as a vector. It's the thing you'd guess would be the definition of the derivative of a vector valued function with respect to t. And luckily it's the correct definition. It gives you the geometrically interesting quantity, the velocity. So you can see one of the things about the velocity vector that's very special is that it's tangent to the curve. Of course that's what derivatives do. They give us tangent lines. And of course the velocity of a particle should be going in the direction of the curve. One of the things we'll talk about is sometimes it's nice to take only the direction information, and so in other words normalize this v vector to be a unit vector and to get just pure direction information. That's going to be called the unit tangent vector. Let's see what else. Let's talk just a little bit about acceleration, just to do one example real quick. Here's the acceleration vector. It's actually a little hard to see because in this case, there we go. It was kind of overlapping with p for the start there. The acceleration vector is just the derivative of the velocity vector. And now that's a little harder to picture, but look at when I toggle between 2 and 2 1/4, look at what the yellow vector is doing. It's moving, its tip is moving inward towards the axis, and you'll see that clearer if I look at it sideways. Then you can see that it's moving purely in towards the axis, and if I go around this way, at every time as it turns, the velocity vector turns towards the axis, and so the difference between the tips of those vectors is the green vector. In the direction of the green vector is the acceleration. Okay, that's just a nice little quick intro, and that'll be good for now.